Okay, so now it's time to talk about electromagnetic radiation. I want to apologize for my voice. I'm a little raspy right now, but we're in the middle of a semester and we simply can't stop. So I've got to keep recording videos and keep on with the conversation. So just bear with me. So we're going to talk about electromagnetic radiation, and this chapter starts out with a figure of the Crab Nebula, which is really cool. This is it looks like it's an explosion of a star. Okay. And importantly, when we analyze this with spectroscopy, we find that there's evidence of sulfur ions in there. This is kind of cool. Let me get my draw thing here. We find that there's evidence of sulfur ions and evidence of O2 ions, which is really unusual. But it turns out we have evidence that there are such ions are in this Crab Nebula, and these two as well. So, and it's because of the spectra that we get. It's not just that it's a particular color, it's that we measure it and we find it has a very precise color. And that color is strong evidence that these things exist. Okay, so I'm going to try to convince you of that in this conversation, or this series of conversations in Chapter 6. All right, so first of all, electromagnetic energy is we need to start out with some basics. Okay, the nature of light has been considered for a long time. All right, in the 17th century, in the 1600s, Isaac Newton found that white light consists of individual colors combined together. So he split light up and found that it was actually a bunch of different colors all put together. Light is composed of streams of extremely tiny particles traveling at high speeds, according to Newton's laws of motion. Okay, now he didn't figure that out. We figured that out later. Okay, light is composed of streams of extremely tiny particles. All right, they're called photons. All right, so early in the 19th century, that's the 1800s, Thomas Young found that light passing through narrow, closely spaced slits produced interference patterns. This is really, really bizarre. Okay, light passing through narrow, closely spaced slits produced interference patterns could not be explained in terms of Newtonian particles. And so it could easily be explained in terms of waves. So we've seen how waves can make interference patterns. If you go out to the sea, see two waves clashing against each other, they interfere constructively or destructively. Right? So Newton suggested that light was particles. Thomas Young suggested that light is waves. Okay, and James Clerk Maxwell said that light was the visible part of a vast spectrum of electromagnetic waves. Okay, so it turns out in the early 1900s, this is a big deal. Particles and waves are connected on a fundamental level, and we say that they are both waves and particles, which is really, in our macro world, it's just impossible to understand. So we're going to appreciate it. We're going to talk about the waves of light, and we're going to talk about the particles of light. But when it comes down to it, I will say that I've had full classes on this in graduate school, and I would say there's still a lot of it I simply don't understand. I believe it, I calculate it, I get the right answers, but I don't deeply understand it. It's just bizarre. All right, so first of all, a wave is an oscillation or periodic movement that can transport energy from one space to another. You've seen waves before: shaking the end of a rope, a guitar string, dropping a pedal into a pond, the expansion of air that accompanies a lightning strike, which makes thunder, right? So these are waves. Whoops, whoa. These are waves. In each of these waves, in each case, kinetic energy is transferred through matter, right? While the matter remains essentially in place. All right? Now, waves are not restricted to travel through only matter. Electromagnetic waves can travel through space, and they consist of an electric field oscillating. This is weird. They consist of an electric field oscillating in step with a perpendicular magnetic field. Again, I definitely don't deeply understand this. I don't expect you guys to understand it either, but I believe it, and I want to tell you about it. And so this will be part of a building block in your understanding of nature, right? So electric field is oscillating. It's perpendicular to a magnetic field. Weird. Both of which are perpendicular to the direction of travel. Okay? Electromagnetic waves can travel through a vacuum at a constant speed, and that speed is the speed of light. It's basically 3 times 10 to the 8 meters per second, right? We go out 3.99. It's actually 3.9979 or something like that, right? So if we go out to a certain number of sig figs, it's basically 3. 3 times 10 to the 8 meters per second. All right, so that is a brief introduction to electromagnetic radiation. Hold on to your hats. There's more to come.